Assalamu alaikum everyone and welcome back to my channel. In our last video, we took a raw dataset, cleaned it and performed a detailed exploratory analysis, ending with a correlation matrix that gave us some key insights. Now a quick heads up. Today's video is all about feature engineering and we will be starting with a cleaned dataset we created last time. To get the absolute most of this video, I highly recommend you to watch the previous video first. It lays the foundation for everything we are about to do. I have put the link right at the top of the description for you. Alright, let's get ready to transform our data and unlock its true predictive power. Let's dive in. As promised, we are starting with the clean data we saved in the last episode. A simple pd.read_csv and we are right back where we left off, ready to build on our work. No cleaning, no basic inspection needed. We can jump straight into the exciting part, creating new features. Our dataset has acceleration readings on the x, y, and z axis. While useful, they are three separate numbers. What if we could combine them into a single, more powerful feature that represents the total vibration? Let's do that. Here we are calculating the root mean square or RMS. This is a standard engineering formula that gives us the magnitude of the vibration vector. Think of it as a measure of the total vibration energy at that instant. We create a new column called vibration RMS to hold this value. Next, we want to capture the single biggest jolt. We take the absolute value of the three accelerations and find the maximum value across the row using dot max method. This gives us the peak vibration, which could be critical for detecting the sudden impacts or stress events. This is where things get really cool. A single temperature or wind speed reading is just one data point. But is that temperature normal for the day? Is the wind picking up? To answer these questions, we need context, which we will get from rolling windows. First, we need a proper date time index for pandas to perform the time based operation. We combine our date and time columns and then set this new date time column as the index of our data frame. Now look at this. We use the rolling method. By passing 2h, we tell pandas to look at a 2-hour window of data for each point. We then calculate the mean to get the average temperature over the last 2 hours. We do the same for our 24-hour window. Since our data is in 50-minute intervals, 24 hours is a 96 data points. So we use window is equal to 96. But we don't stop there. We then create the deviation features by subtracting these averages from the current temperature. This tells a model not just what the temperature is, but how it compares to the recent and daily averages. A large deviation could be a sign of sudden weather change. We apply the same logic to wind speed, calculating both the average wind and the max wind speed over the 2-hour and 1-day windows. This allows our model to distinguish between steady wind and the sudden, potentially damaging gusts. Okay, we have created a whole suite of powerful new features. Our data frame has expanded from its original set of columns to include all this new contextual information. A quick call to df.info confirms it. Look at that. We now have 23 columns. We have successfully added our vibration, temperature, and wind features, and they are all clean with no null values. Now, just because we created a lot of feature doesn't mean we have to use all of them. The next crucial step is feature selection. We need to decide which columns will actually go into our model. We will also formally separate our features from our targets. Here I am creating a Python list that contains the names of all the columns I want to use as predictors. You will notice that I am including our new engineered features like vibration RMS and average temperature to R. I am also keeping some of the original powerful predictors we identified earlier like degradation score and FFT magnitude. I'm deliberately leaving out the original acceleration columns because we have replaced them with the more informative RMS and peak features. And here we create a new data frame called targets. This explicitly separates the columns we want our model to predict. This is a great practice for keeping your code clean and organized. We have made a lot of changes. It's time for one final check to see how our new engineered features relate to each other. This is important to check for multicollinearity, where features are so highly related with each other that they become redundant. Our model can sometimes get confused by this. The same correlation and heat map code as in our last video, but this time we are only passing in our final list of selected features. This is exactly what we want you to see. Let's look at some key areas. Vibration RMS and peak vibration have a very high correlation of 0.96. This makes sense. They are derived from the same source data. For some models, we might choose to keep only one of these to avoid redundancy. Similarly, wind average 2 hour and wind average 1 day are highly correlated. This is logical. And importantly, we can still see the strong relationship between the degradation score and forecast score next 30 days at 0.98. This final check gives us confidence in the set of features we have chosen to move forward with. This is it, the culmination of all our work. We have a dataset that is clean, rich with engineered features, and ready for a machine learning model. Let's save it. We used the 2CSV method one last time to save our final data frame. I'm calling it featured dataset v2. Now, when we start our modeling script, we can load this file and know that it contains the absolute best version of our data. And that's a wrap on feature engineering. We started with clean dataset, brainstormed and created new features based on domain knowledge, and ended with a final curated set of predictors ready for action. We have transformed our data from simple sensor readings into a rich and contextualized dataset. This process is often the difference between a mediocre model and a high performing one. I really hope that gives you a clear idea of how you can apply these techniques to your own projects. Thank you so much for joining me. In the next video, we will finally use this featured dataset V2 to train a machine learning model to predict the bridge damage. You won't want to miss that, so be sure to subscribe. If you have any questions, drop them in the comments below. I will see you in the next one.